In this video, I'm going to present a research paper summary on the paper Group Normalization from 2018. Recently, I've been working to create a model or a set of models that perform well on the Imagenette dataset from FastAI. And I realized that as the batch size got smaller, I was getting better results. However, there's also some complexities to how training performs when you use a small batch size. So I had a conversation with Google Gemini's deep research feature, and it made a report, and one of the things that it recommended was to use group normalization, since in the paper it referenced a very significant performance boost when using group normalization instead of batch normalization. So that motivated me to read this paper, and that's why I'm presenting it here. Here's my outline. I'm going to start with main takeaways. Then I'm going to do a high-level overview that kind of focuses on the abstract and introduction. I'm going to go through batch normalization review very briefly. I did not read the full paper, but I understood enough of it that I can explain some of the key concepts. I'm going to then introduce the paper's motivation for group normalization, walk through the different mean and variance calculations for different normalization methods, give some screenshots of what the group normalization code looks like, talk about their experimental setup, and then end with results. So I had four main takeaways. Batch normalization, which is referred to as BN in this slideshow, calculates mean and variance statistics across images in a batch, and thus requires a running average of these statistics for use in inference. And that inference is also during the training when you're using the validation set to calculate accuracy, for example. Batch normalization used in small batch size training leads to noisy statistics and worse performance. Group normalization, GN, calculates mean and variance for a group of channels for a single image, so it's independent of batch size, and so it's not looking across the batch, and it performs consistently for a wide range of batch sizes. A wide number of groups and number of channels per group for group normalization perform pretty well, as long as the values are greater than 1. All right, so let's look at an overview and kind of look at end-to-end what group normalization is. So this is from the abstract. Batch normalization's error increases rapidly when the batch size becomes smaller, caused by inaccurate batch statistics estimation. Group normalization divides the channels into groups and computes within each group the mean and variance for normalization, and this is independent of the batch. Group normalization is proposed as a layer that divides channels or features into groups and normalizes the features within each group for a single image. And it does not exploit the batch dimension. So this was the, figure 1 that shows Imagenette classification error versus batch sizes. This is for a ResNet 50 model using 8 GPUs. And we have the blue plus marker, which is our batch norm, and the red circle marker, open circle, which is group norm. And as we can see, group norm accuracy or error rate is consistent no matter what the batch size is. Whereas for batch norm, even though it beats out group norm at higher batch sizes, as the batch size gets lower, the error rate gets significantly worse. And so in situations where we have to use a small batch size, whether it's a memory constraint or it could also just be a preference, because we find that, as I did in the Imagenette case, a smaller batch size performs better. Batch norm is going to introduce this noise in the estimates of mean and variance statistics, and that's going to ultimately worsen the performance of the model. This was a figure that took me a minute to understand, but once I did, it's a really nice way to visualize the 4 different normalization methods that they discuss. So we're just going to go left to right and top to bottom in this table. So first we have batch norm. And in batch norm, all pixels in one channel across all images in the batch are used for mean variance calculations. So if we look at the dimensions of this cube, we have n, which is the batch size. So here, if we take this grid literally, we have 6 images. C is the number of channels or features. So we have 6 channels. So maybe we have like vertical edge detector, a horizontal edge detector, a diagonal edge detector, so on. And then we have this like unrolled height and width dimension. So just for the sake of an example, let's say we had a 2 by 3 image. If we unrolled that, we would get 6 pixels, and that's what we have in this dimension here. So what's highlighted here is a single channel across all 6 images in this batch, across all 6 dimensions in each image. So that's batch norm. It normalizes per channel across the batch. It is batch dependent. The second one is layer norm. In layer norm, all pixels in all channels for a single image are used for the mean variance calculation. So it's not including the batch. It normalizes each image's entire feature map. This is batch independent. So each image gets handled separately. So it doesn't matter if there's 2 images or 32 images. The normalization happens perpendicular to the batch dimension. Okay, then we have instance norm, which is, as its name suggests, all pixels in one channel for one image. So we have all 6 pixels, but we only have one image that's being activated for this calculation, and we only have one channel or one feature that's being activated. And finally, we have group norm, which is the topic of this paper, where all pixels in a group of channels for a single image are used for mean variance calculations. So group norm is somewhere in between instance norm and layer norm, right? Instance norm, we have one channel and one group. Layer norm, we have all channels in one group. In group norm, we have, in this case, 3 channels in one group and 3 channels in the other group. And so it kind of breaks up the features into these groups. So as the key idea mentions, a compromise between layer and instance norm, again, batch independent. It's only doing it for a single image. So it doesn't matter if there's 2 images or 32 images. It's processing only one image for the mean variance calculation. All right, so hopefully that sets up a good foundational understanding of what we're talking about when we talk about these different norms and these different dimensions. Something I should have started with is that N is the batch axis, which I think I talked about it, but C is the channel axis and H and W are the spatial axes. Yeah, we already talked about that. Throughout this presentation, I'm going to show some code and look at the shapes of tensors, so we'll also get a look at what that looks like tangibly. For example, here we have batch norm, all pixels in one channel across all images in the batch. So I'm using the batch norm 2D that's inside the ResNet, mainly because in the Imagenette practice that I'm doing, I'm using the XResNet 18, and I want to get more familiar with the model, so I figured I would use the batch norm layer. And it has 128 features or channels. So I have some input which has shape N by C by H by W. So I have 32 items in the batch, 128 channels, and let's assume that these are 256 by 256 images. So I pass that input through my batch norm 2D layer. I get back an output of the same shape. And then to illustrate which pixels are used for the mean variance calculation, I'm going to take all pixels, so all 32, so across all images in the batch, so I'm taking all 32 images, one channel, so I'm taking the first channel, which is the second dimension, and then all pixels in the images, which is 256 by 256. So I take the mean of that, and then I look at the variance of that, and as you can see here, the mean is effectively 0, and the variance is 1.0000. So this is our evidence that we are normalizing all pixels in one channel across all images in the batch, and that is batch normalization. Next, we have layer normalization, all pixels in all channels for a single image. So again, we have the same output shape. We have 32 by 128 by 256 by 256, and we're going to take that first image, and we're going to look at all channels, all 128, across all pixels. We take the mean and the variance, and again we see 0 mean and 1.0000 as our variance. All right, so that's layer normalization. It's taking the mean across all features. Okay, next we have instance norm, all pixels in one channel for one image. So we take one image out of the 32, we take one channel out of 128, and then we keep the 256 by 256 dimension, and then we take the mean and the variance, and we can see that it's 0 and 1.0000. If I took the last image out of 32 and the last channel out of 128, we can also see the mean is 0 and variance is 1. So again, just kind of intuitively building tangibly an understanding of how these different shapes are normalized. And finally, we have the star of the show. We have group norm, all pixels in a group of channels for a single image. Right? So here's a single image. We take the first one out of 32. We take the group of channels. So I chose G, which is groups, number of groups, as 32, which is the default in the paper. 128 divided by 32 groups gives you 4 channels per group. So I'm looking at the first 4, and then I'm looking at 256 by 256. And again, we see that the mean is 0 and the variance is 1. So that's the last example I have in terms of looking at this code. All right, so the group normalization paper is really introduced as a alternative to batch normalization. So I wanted to make sure I at least understand some basic things about batch normalization. So we're going to do a quick review referencing the batch normalization paper. So this is summary generated by Gemini Pro after a conversation that I had, and I kind of edited it. It was a bit longer. It was probably twice the length of what it is here. So there's 3 aspects we're going to look at: batch normalization during the training step, batch normalization during the evaluation step within the training loop, and then batch normalization after training is complete for final inference. So during the training step, per batch statistics are used to normalize the images in the batch. And we'll look at algorithm 1 in the next couple slides. So key thing is per batch statistic, as we saw in the previous example. And just to show the example, if we go back up here, I'm taking all 32 images. 32, here we go. So this colon is saying per batch. All right, during the evaluation step, there is a running moving average that batch normalization stores, and it's updated with the per batch statistics from the training steps, and that's used to normalize the images during inference. And the batch normalization paper states, using moving averages, we can track the accuracy of a model as it trains. And we'll take a look at what that moving average looks like in PyTorch, at least just at a high level. And then finally, after training is complete, the final running averages of mean and variance are combined with the learned parameters gamma and beta to create a single efficient linear transformation. And we'll see that this process is in algorithm 2, steps 10 and 11. So key idea is that the statistics that are used for inference are based on this running moving average, either up to the point of the evaluation step, as it is within the evaluation during training loop, or throughout at the end of the final training with all of the batches statistics updating the moving average for the final inference. Here is batch norm 2D in the PyTorch documentation, and I'm highlighting this momentum argument. This is different from the one used in optimizer classes and the conventional notion of momentum. Mathematically, the update rule for running statistics here, so in the case of batch norm, is that the new average, the new x is 1 minus momentum times x plus plus momentum times x, where x hat is the estimated statistic and xt is the new observed value. So x hat new, for example, is our new mean. That's 1 minus momentum times the current moving average of the mean plus momentum times the new per batch mean statistic that we calculated. So this is how it keeps updating. And the same thing for the variance. Our new variance is 1 minus momentum times the current variance, that's the moving average, plus momentum times the new observed value of variance that's based on whatever the last batch was during training. And this track running stats argument is by default, is true. Okay, So looking at it a little more closely in terms of the calculation of mean and standard deviation for batch norm, we have this mu I, which is for a given item or for a given batch. And then we have 1 over m taking the sum of the pixels. And we have this k value that is a part of this s value, which we'll talk about in a second. And then here we have our variance, 1 over m. Again, we have k as part of this set psi, and we're taking the summation of the item, the mean squared, plus some epsilon value, so that we don't have like a 0 value for or any kind of explosion. I think that's why we have this epsilon. Yeah, this epsilon generally is like just to make sure that there's no numerical issues with our calculation. So SI is the set of pixels in which the mean and standard deviation are computed. And M is the size of this set. So if we look at this image, the set of pixels that we are concerned about are, as defined here, S is the index K, where KC equals IC. So IC is the index of all of the pixels in the entire cube, but we are looking at just that slice where we're looking at the pixels inside of one channel. So IC and KC denotes the subindex of I and K along the C axis. So for example, here we have 6 times 6, we have 36 different pixels that we see here. And so KC is going to go through, 0 to 35. This means that the pixels sharing the same channel index are normalized together, right? So per channel normalization across the batch, across the dimensions of the image in this case. For each channel, batch normalization computes mean and variance along the N, HW axes. Okay, so this idea of set S, which is going to be what is the kind of subset of the full set of pixels that we're considering, we're going to see this for the other normalization layers as well. This is looking at the same thing we saw a bit ago, but just kind of going over it again. The normalization takes place across the batch for a single channel across all pixels of those images, and the mean is 0 and the variance is 1.0000. And here we can see momentum is 0.1 and track running stats is true for this XResNet 18 layer batch norm layer. Cool. So this is algorithm 1 from the batch norm paper, where we're basically just looking at some math laid out here. The mini batch mean is updated by going through from 1 through m, which is the number of items in the mini batch B. The mini batch variance is going through those items and calculating the mean minus, or the item minus the mean squared. And then we normalize, so we subtract the mean value from each pixel, and then we divide by the square root of variance squared plus epsilon. And then the final piece is that we have two learned parameters, gamma and beta. Gamma gets multiplied by the normalized input, and then beta gets added on. And that's what we're calling the output of our batch normalization of our xi given our gamma and beta learned parameters. So again, this capital B is the mini batch. X are the items in the mini batch, the images, and we're subtracting and averaging to get our variance and mean. So this is what happens during training. We are getting per batch statistics. Algorithm 2 is looking at the entire batch normalized network training. So if we look at this first piece, we see that algorithm 1 is referenced here. And then this piece here, we have trained our network. Let's say we've trained it for a certain number of steps, and we have now frozen our parameters because we're going to use it in inference. During inference, we process multiple training mini batches, each of size m, and we average over them. So here's our running average, where however many batches have been trained, we are going to average all of those means and all of those variances to get our running average mean and running average variance. And then we kind of do two things. We do the normalization and we do the linear transformation together. And we'll look at that math in a second. But just going back here, once the network has been trained, we use the normalization shown here using the population rather than the mini-batch statistics. So population meaning all of the mini-batch statistics average. Using moving averages, we can track the accuracy of a model as it trains. Since the means and the variances are fixed during inference, the normalization is simply a linear transform applied to each activation, which is this guy down here in step 11, and it may further be composed with the scaling by gamma and shift by b to yield a single linear transformation that replaces the batch norm function. And we'll look at that combined transformation. So we're going to start with our fixed inference statistics. So here's x hat, which is our normalized x given the running average of our mean and then the running average of our variance. Our learn parameters create a linear transformation, gamma x hat plus beta. We're now going to plug in this value of x hat, our normalized x, into gamma x hat here. So we're just dropping this in. We're going to distribute this gamma. So we get gamma x over the square root of the variance minus gamma times the moving average of our mean divided by square root of variance plus beta. And then we're just going to reorganize a little bit. We're going to move this x down here so it looks more of like y equals slope times x plus intercept. And then we're going to group these two terms, beta minus gamma moving average of mean divided by square root of moving average of variance. So we get this y equals mx plus b form. So that's what we're looking at during inference. We have a single layer that we apply to the input, and we normalize, scale, and shift in one operation or in one formula. Another note from Gemini, for small batch sizes, per batch statistics become noisy. So one or two images might be outliers, which will drastically skew the mean and variance for that batch. Moving average of statistics become noisy. A series of unstable, high variance updates will cause the moving average to be a less reliable estimate of the true population statistics. So you can imagine if I have one particularly outlier image and it's in a batch size of 2, its weight in terms of how much it contributes to the batch norm statistics, the mean and the average, is 50%. However, if I had 32 items in the batch and I had one outlier, now it contributes 1 over 32. So it's significantly, it's 16 times less impactful to the overall batch statistics. And so as we decrease our batch sizes, the per batch statistics is the source of the noise, and then that has a downstream effect on the moving average of our statistics, which also becomes noisy. All right, so that's a quick review of batch normalization. Next, we're going to look into the motivation for group normalization as is stated in the paper. So they talk about this idea that it's not necessary to think of our features or channels as unstructured vectors. For example, it is reasonable to expect a filter and its horizontal flipping to exhibit similar distributions of filter responses on natural images. That sentence I think is a little more confusing, but this next sentence I think is a little more clear. If this conv1 layer happens to approximately learn this pair of filters, so we have some filter and then we have the horizontal flipped version of that filter, or if the horizontal flipping or other transformations is made into the architectures by design, then the corresponding channels of these filters can be normalized together. So this was the motivation. We're going to tease it out with the help of Gemini and tease out the main ideas with the help of Gemini. So there's three things. There's the premise, which is the data. There's the consequence for the mean, and then the consequence for the variance. So the premise is that in the universe of natural images, there is no inherent bias for example, right slanting edges over left slanting edges. They appear roughly equally often. So the consequence for the mean is that since both type of edges are equally common, the filter in our convolution layer that detects the right slanting edges and the filter that detects left slanting edges will on average be excited by the same amount when looking at a large number of images. So the mean activation, which is the excitement of the neurons through the use of the filter, are expected to be similar. So what this is basically saying is that on average, the pixels that are activated for these different filters, on average, are going to be equal across these different features that are roughly, equally as frequently appearing in an image. So the consequence for the variance is that the spread of activation values should be similar. What does that mean? Both filters will encounter regions of strong matches, high values, weak matches, medium values, and no matches, low values, in similar proportions throughout the dataset. This means that the variance will also be similar. So it's just as likely that right slanting edges are sometimes appearing very sharply or very subdued or not at all, as left slanting edges are in the dataset. Okay, so basically this idea is that there's no kind of hierarchy when it comes to, or bias when it comes to some of these features. And so we can start to think that these features are kind of equally important when it comes to being activated on the image. They also go on to say that higher level layers are more abstract and their behaviors are not as intuitive. However, in addition to orientations, such as horizontal, vertical, left slant, right slant, there are many factors that could lead to grouping. For example, frequency, shapes, illumination, textures. Their coefficients can be interdependent. So now this is moving a step forward and saying, all these different features are roughly equally likely to happen. On average, they're activating the same amount of pixels, and on average, they're about spread out the same. What they're now saying is that there are some, inherent grouping of channels, whether it's by frequency, whether it's by the shapes that they contain, whether it's by all of them being related to illumination or all the channels being related to textures. And so the fact that there's these groupings of channels means that their coefficients, or the statistics that are generated by them, by those pixels, are interdependent. So we're going to return to that concept a little later on with some help with Gemini, but I want to now go into the mean and variance calculations, not just for batch norm, but for batch norm, layer norm, instance norm, and the star of the show, group norm. So here's a general formulation of feature normalization. All of these, batch norm, layer norm, instance norm, and group norm, perform the following computation. We have some x, the feature computed by a layer. I is the index. In the case of 2D images, I has these 4 coordinates, which is the batch item, the channel, the location in the height of the image, and the location in the width. So think of it as 1 pixel, and that's xi, and this index is a 4D vector. And so we're subtracting from that, we're subtracting the average pixel, and then we're dividing by the standard deviation. And that gives us our normalized pixel. Again, x is the feature computed by a layer, and I is the index. So if we look at how these different normalization methods are approaching this, they're all looking at a different subset. So S is the set of pixels in which the mean and standard deviation are computed, and M is the size of this set. So as we'll see in some cases, the S, the set of pixels, is all the channels, or all the images, or it's a group of channels, or it's a single image. So the set of pixels that we're summing across here and we're summing across here, that set of pixels is dependent on whatever strategy we're approaching. Gemini Pro says the indices I and K serve 2 different purposes. I points to the target pixel you want to normalize, and K is used to loop over the group of pixels needed for the calculation. So I is kind of like the universal index, and K is the kind of local specialized index for the particular strategy of normalization that you are picking. Okay, we already looked at batch norm, but we can look at it again. We are looking for the K index such that K is inside a single channel. So here we have channel index 0. So if we go back up here, IN, IC, IH, IW, we are looking at K values that are fixed for a given channel. And then we're iterating on the batch item, and then we're iterating on H and W. So we go back down here, fixed channel, so index 0. We're iterating on N to go from batch item 0, 1, 2, 3, 4, 5. And then we are iterating through our H and W dimensions to go through pixel 0, 1, 2, 3, 4, 5, 6, or 0, 1, 2, 3, 4, 5. So this is our subset of the entire set of pixels I. We're kind of fixing the channel index. Again, this means that the pixels sharing the same channel index are normalized together. Here is layer norm. This is now fixing the batch item. So that means that this computes mu and sigma along the C, H, and W axes for each sample. So again, the subset here that we're fixing is the particular batch item, which is a single image, all channels, all pixels. Next, we have instance norm. So we're fixing a single image, so Kn equals In, and we're fixing a single channel, Kc equals Ic. So it only computes the mu and sigma along the H and W axes, so across the 6 pixels in the image in this example. In all these cases, there is a final per channel linear transformation with learned parameters gamma and beta. That is also the case for group norm, which we're going to see next. So here we go. Group norm is a little more involved, so I've just put the explanation because it's a little easier to parse than the actual formula. But we are fixing one item in the batch at a time. So we're looking at one image at a time. There's the batch independence. And then we're looking at each set of channels in a given group at one time. So G is the number of groups, 32 by default. C divided by G, so channels divided by groups, is the number of channels per group. This is the floor operation. And this Kc over C divided by G equals Ic over C divided by G. What it means is that the indexes I and K are in the same group of channels, assuming each group of channels are stored in a sequential order across the C axis. So our group norm computes mu and sigma along the H and W axes and along a group of C over G channels. So easier to see here. So again, assuming each group of channels are stored in a sequential order. So we're going in a sequential order down the C axis, 3 channels at a time. And then we are taking the mean and variance of all the pixels in this 3-channel group for a single image. The pixels in the same group are normalized together by the same mu and sigma. So again, single image, multiple channels, all the pixels in the image. Group normalization also learns the per channel gamma and beta, as the other ones do as well. Okay, going back to some of the relationships between group normalization and other normalization techniques. So group normalization becomes layer normalization if we set the group number as G equals 1. So in that case, C divided by G is just C, and we're looking at all the channels, which means we're looking at the layer norm situation. They also say that group norm is less restricted than layer norm because each group of channels are assumed to subject to the shared mean and variance. The model still has flexibility of learning a different distribution for each group. So remember, the mean and the sigma are only calculated for that group. So the model can learn different mean and variances for the different groups of channels. So it has this kind of more flexibility of learning different things. And then when we look at instance normalization, group norm becomes instance norm if we set the group number as G equals C. So 1 channel per group. So here is instance norm. Here is 1 channel per group and across 1 single image. What they say here, and this was interesting, and this kind of goes back to the motivation of group normalization. In instance norm, we can only rely on the spatial dimension for computing the mean and variance. It misses the opportunity of exploiting the channel dependence. So this idea that there's these like inherent groups of channels where a set of channels are about shapes, a set of channels are about textures, a set of channels about illumination, and so on. And Gemini says channel dependence is the idea that different channels in a convolutional layer are often not independent. They can have statistical relationships with each other because there's something about them that relates. Maybe slanted lines and horizontal lines have some shared notion of horizontalness of a feature. Okay, so we have an understanding of how the mean and variance are calculated for group normalization as well as the other ones. Let's actually take a look at some code. This is the example they gave in the paper from TensorFlow. We have a group norm method, a function. It takes the input x, it takes the gamma and beta learned parameters, it takes the number of groups g, and it takes a small value epsilon. So first we pull out the dimensions from x.shape. So number of items in the batch, number of channels, height, pixels, and width pixels. We take this channel dimension and we reshape it into number of groups, comma, number of channels per group. So if this was 128 and we had 4 groups, this 128 would be split into 4, comma 32, if we had 32 channels per group. Then when we take the mean and variance, we're taking it across the 2, 3, 4 indexes. So here's index 0, here's index 1, 2, 3, 4 is the channels per group, the height, and the width. And that again goes back here, channels per group, height, and width. So those are the dimensions, those 3 dimensions. C, H, W are the 3 dimensions that are actually used during the calculation of our mean and variance. We actually do the normalization. We subtract x, or mean from x, and key point is that keep dimensions equals true. So we can broadcast the mean and variance across all of the pixels. And then we divide by the square root of variance plus epsilon. We reshape this back from number of groups and channels per group back to number of channels. And then we return back with x times the learned gamma plus the learned beta. Just as an exercise, I did this using PyTorch in Colab. So I extract the dimensions from x.shape. Here I use a number of groups of 32. I reshape x accordingly. So now it's 32 items in a batch, 32 groups of 4 channels per group, and 256 by 256 pixels in my images. I use the varmean method in Torch, giving it dimensions 2, 3, 4, and I want to keep the dimensions. So keeping the dimensions keeps this 32 images, 32 groups, and then 1 by 1 by 1. And when it comes to number of channels per group, height and width, I then subtract that from our x divided by Torch square root of variance, reshape it back into the 4 dimensions, have some fake values for gamma and beta, and then I have my final y value that gets returned out of the group norm layer. Here is the documentation from PyTorch on group norm. And something that I wanted to highlight is that this layer uses statistics computed from input data in both training and evaluation modes. So there's no running average that is used because we're just looking at a single image across the number of channels and the height times width pixels. And that comes directly from the input data. That doesn't come from any kind of moving average. And this here shows the relationship. So between instance norm and group norm, if we had 6 channels into 6 groups, we would have 1 channel per image. If we had 1 group with 6 channels, this would be equivalent to layer norm. And those are just kind of a different tangible way to look at those relationships. Okay, let's go into this experimental setup, and then we'll follow that by results, and then we'll wrap up. So they use the Imagenette classification dataset with 1,000 classes on 1.28 million training images. Then they evaluate on 50,000 validation images, and they use ResNet models. They use an approach to calculate the mean and variance within each GPU for batch norm. They use 1 to initialize all gamma parameters except the last layer. They have a weight decay value. They train for 100 epochs and decrease the learning rate as the training goes on. And then they evaluate top 1 classification error on the center crops of 224 by 224 pixels in the validation set. They do this learning rate scaling, which is where they use a learning rate of 0.1 for a batch size of 32, and then they scale that up or down based on the batch size that they're using for different batch sizes of n. So for example, a batch size of 16 would use 0.05, which is 0.1 times 16 over 32. All right, let's look at the results. The baseline results that we're going to look at has a G value of 32, and they also use a batch size of 32 images because batch norm works successfully, and so that's their baseline. So what we're looking at here is all trained on a batch size of 32. They have the train error on the left and the validation error on the right. In both cases, the kind of, well, actually not in both cases, but in the validation case, instance norm is the worst, then layer norm is better, group norm is better, and finally batch norm is better. In the training case, instance norm is also the worst, layer norm is second worst, batch norm here is third worst, and the best case is group norm. So group norm actually has a better training error, but batch norm has a better validation error, which is what we're more interested in. This is just capturing those values in table form. The slightly higher validation error of group norm implies that group norm loses some regularization ability of batch norm. And this is because batch norm's mean and variance computation introduces the uncertainty caused by the stochastic batch sampling. So because your batch is a random set of images and there's multiple mini batches, there's this kind of randomness that's introduced, this kind of noise, and you introduce noise, it's going to generalize a bit better at the end, and that's the concept that they're introducing here or discussing here. One thing that I want to keep in mind is that they recommend that for group norm, you can combine it with a regularizer to kind of bring back some of that regularization that the noise in the batch normalization was doing, and maybe that'll improve the results. So future research topic, I'm sure someone's done it, certainly something I'll want to explore. This is now looking at what we are really interested in, which is what happens to batch norm and group norm's validation error as we change the batch size. So here, as we go from blue, dark blue to light blue, which is 32 batch size to a batch size of 2, the error rate goes from 23% up to 35%. So almost a 50% increase. Whereas for group norm, we can see that no matter what the batch size is, the error rate is pretty constant. So it's very robust to changes in the batch size, and it's stable and giving good performance at very small batch sizes, such as a batch size of 2. This is more quantitatively looking at it. For a batch size of 2, you get a 10.6% decrease in error rate when you use group normalization. So that's almost a 30% improvement over batch normalization. They also talk about how in batch norm, if you were to have one image in the batch, this stochasticity that we got from having multiple images would disappear. And in that case, batch norm becomes similar to instance norm at training time. So if we look at instance norm here, instance norm had a 28.4 accuracy. A batch size of 2 with batch norm had a 28.4 error rate, and this was a 34.7% error rate. So instance norm, which is batch norm with a single image, performs better than batch norm with a batch size of 2. And finally, the last kind of takeaway from their results was that this training approach of group norm is pretty robust when it comes to the number of groups or the channels per group hyperparameters. As long as you don't have one group, which is layer norm, or one channel per group, which is instance norm, as long as you have something greater than one, there is some variance, but it's quite robust. So that's nice to see that you don't actually have to really test out these different hyperparameters. It looks like almost anything will be pretty decent. All right, so returning back to my main takeaways, batch normalization calculates mean and variance statistics across images in the batch and as a running average across batches, which is used for inference. Batch normalization used in small batch size training leads to noisy statistics and worse performance. Group normalization calculates mean and variance for a group of channels for a single image, independent of the batch size, and performs consistently for a wide range of batch sizes because of this independence. And a wide number of groups and number of channels per group for group normalization perform well as long as there are greater than one. And I think one thing I'll add is that group normalization takes advantage of this interdependence between channels that we lose in the situation of instance normalization. The two things that I want to take away from my Imagenette experiments is that I'm going to work on replacing batch normalization with group normalization in my three models so that I can use it for smaller batch sizes where I was getting better performance. And then I want to try different regularization techniques with group norm so that that lost stochasticity from batches in the batch norm that we miss out on, we're introducing the regularization with group norm to kind of recapture some of that generalization and hopefully get a better result in terms of validation error. And that is it for this video. Again, this is all part of my Imagenette experiments, so I'll be definitely doing a couple more videos probably in the next 2 days, and I expect a few more as I try to get a high-performance image recognition model trained. So thanks for watching. Make sure to like, comment, subscribe, and I will see you next time.